Here we are going to solve a couple of examples on the Zener diode. And again, as we explained in the previous video, the Zener diode, if you are going to assume it is working in the forward bias region, then you deal with it as a regular diode, just as a regular diode. You can use one of the models that we learned in the previously with the regular diode, the constant voltage drop model, the piecewise linear model, or the ideal diode. However, if you assume that it is working in the breakdown region, then you have to assume the model of the breakdown region, which we defined as a battery and a resistor, but the battery now, its direction is opposite to the battery of the forward bias region. The battery is always opposite to the current that is flowing in the diode. If the current in the breakdown region, the current flowing in the diode will be going in this direction, then the battery direction will be trying to push opposite to the current. Okay, remember that. So now let's take a very simple circuit. We have a source 20 volt, 5 kilo ohm, and we have a Zener diode here. This is the symbol. I forgot to say that maybe in the previous video. The symbol of the Zener diode, we have these two inclined lines at the end of the line. This is the difference between the symbol of the regular diode and the Zener diode. The regular diode, it looks like this, just a dash here. The Zener diode, we have this like a Z, letter Z at the cathode. Okay, so these are this is the difference between the symbol of the Zener and the symbol for the regular. So we have a Zener diode, and it's given that VZO is 5, RZ is 100. Okay, sometimes the problem also gives you the characteristics of the Zener diode in the forward direction. For example, it says that in the forward direction, VDO will be 0.7 and our diode will be, for example, 10 ohms. So it gives you the characteristics of the forward and gives you the characteristics of the breakdown. So these are the characteristics of the breakdown. VZO is 5, and as we agreed, VZO, this is the battery value, and RZ, this is the resistance value for the model in the breakdown region. So here it's kind of obvious that the source will be trying to push the current in the opposite direction. So this diode either will be reverse bias off or it will be breakdown. And there is a condition for the breakdown that we need to check, is that I Zener, for the breakdown condition, I Zener must be greater than or equal of I Zener K. This is the minimum point for breakdown. I Zener K is not given in this problem. So what should we do? If it is not given, we said that by default you take it 0. So the condition for breakdown here in our problem that we need to verify is that I Zener must be greater than 0. Now let's solve this problem. What we will do is we are going to replace the Zener diode with the breakdown model. We'll say assume breakdown. Then when we assume breakdown, we are going to replace the Zener diode with the breakdown model. And the breakdown model is a resistance and then a battery in this direction. This battery is VZO, which is given to be 5 volt. This resistance RZ is 100 ohm, and this resistance is 5 kilo ohm. Now, let's calculate the current in this circuit. The current in this circuit will be 20 minus 5 over the total resistance, which is 5 kilo ohm plus 100 ohm. This is 15 over 5.1 kilo ohm, which will give you I Zener to be 2.94 milliampere. As we see here, I here is the same as I Zener, right? The current in the circuit, is the same as I Zener in the diode. It's same as I Zener in the diode, going in the opposite direction of the diode, right? I Zener. So I Zener here is greater than 0, then we say that our assumption is correct. And we can, I can ask you anything after that. I can ask you to calculate V Zener. V Zener is the voltage across the diode. V Zener is defined as VZO. V Zener is the voltage, the whole voltage across the diode in this direction. V Zener equals VZO plus I Zener, R Zener. We already have R Zener, 100 ohm or 0.1 kilo ohm. We multiply by I Zener, which is 2.94 milli. We always, if you use the current with milli, you multiply by the resistor in kilo ohm, so that the result will be in volts. So you can use the current in milli and the resistance in kilo ohm, so that when you multiply, the kilo will cancel the milli and you will get a volt. Plus VZO, which is, VZO is 5, then this will give you 5.294 volt. So the voltage across the Zener diode here will be 5.294 volt, and that's it for this simple problem. Let's look at another problem. So we have a problem here with supply voltage 20, resistance again 5 kilo, and then we have a Zener diode here, VZO5, and I'm giving you that the Zener resistance is 0 ohm. By the way, when I give you that the Zener resistance is 0 ohm, this means what in the characteristics of the Zener diode? This means that the breakdown region, when breakdown happens, the slope of the line will be infinity, right? Because the slope of the line is 1 over the resistance. If the resistance is 0, then the slope of the line will be infinity, which means that the line will be vertical. The line will be vertical at negative VZO, right? Which means that this is an ideal, this is a perfect regulator. Why perfect regulator? Why are we using the Zener diode from the beginning as a regulator? Because in the breakdown region, the voltage of the Zener diode approximately is constant. Even if there is a resistance, approximately the voltage will be constant. It's like a battery. That's why you model it as a battery and the resistor sometimes, and the resistor is very small. Okay? Sometimes you can model the resistance, since it's very small, you can model it to be 0. And in this case, in the breakdown region, the Zener diode will work as a perfect battery. No resistance, only battery. Okay? With a Zener voltage, VZO, which is here, will be 5 volt, perfect battery. That's why we use the Zener as a regulator. For example, here, when the Zener diode works as a battery in the breakdown region, it will provide to your load, your computer or your TV, it will provide a constant voltage to your TV, 5 volt constant, right? Even if this source voltage changes a little bit, goes up or down a little bit, there is fluctuations in this voltage, then it will not affect your load. Your load will see always a battery voltage of 5 volt. This is the meaning of a regulator, right? So here, let's go back to our example, and you will see that we'll assume breakdown. We'll assume breakdown. Then, if we assume breakdown, we replace the Zener diode with the model. Here, the model will be only a battery because the resistance is 0, right? So the resistance RZ is 0, so it will be only a battery of 5 volt. Then here, this is your load, your TV, your computer. Our load is 5 kilo ohm, and this is 5 kilo ohm. And then this resistance also is very important. It has to be there in the circuit. Why is that? Because if the voltage, if the source voltage fluctuates, goes up or down, and you need here a constant voltage, who will take the difference? Who will take the difference between this voltage that is changing up and down and this constant voltage? The resistance here. The resistance here will take the difference between this fluctuating voltage and this constant voltage. So this resistance is very important. If there is no resistance here, then the Zener diode will be forced to change the voltage on it. So this resistance is going to take all the fluctuations all the changes in this voltage, and it will guarantee that the voltage of the Zener will be constant, okay? So here, this is our source. Our source is 20 volt. And this is now our circuit, assuming breakdown. Assume breakdown. You have to say your assumption, don't forget. Assuming breakdown. There is no resistance because RZ is 0, as we said. And now, what is required is to find the output voltage and the minimum load resistance for the Zener diode regulator shown below. We'll come to this after we solve the first part. So we need the output voltage. The output voltage is the voltage across the load, right? As you see here, the voltage across the load will be 5 volt because we don't have a resistance here. We have only a battery between these 2 points. So the output voltage will be constant of 5 volt. Now, the second part of the question is asking you about the minimum load resistance for the Zener diode, the minimum value of this load resistance. Before we solve this part, we ask ourselves, why there is a minimum? Why there is a minimum? Like before we solve this part, did we miss something? We calculated V output. Did we miss anything? Yes, we missed one step. We missed the verification. So if you reach this step and you stop, then you will not take the full mark. Why? Because you need to verify that your assumption of breakdown is correct. How to verify this? You have to verify using our rule that I Zener is greater than or equal IZK. IZK is not given here, right? IZK is not given here. So by default, as we said, if it is not given, you take it to be 0. In order to calculate IZK or Zener, we need to calculate the current here. How to calculate the current here? We know that the voltage here is 5 volt. This is the output voltage, 5 volt. Right? So what we can do is, we can say that the current going in this direction equals the 2 currents entering the node, right? So the current I Zener, we can say that the current I Zener equals what? Equals 20 minus 5 equals the current going in this direction plus the current going in this direction. 20 minus 5 over 5. 20 minus 5 volt over 5 kilo ohm plus the current going in this direction. The current going in this direction is 0 minus 5. 0 minus 5, 0 the ground, minus 5 volt over this resistance which is 5 kilo ohm. So here it will be 15 over 5, this is 3 milliampere, minus 1 milliampere, it will be 2 milliampere, this is the Zener current, greater than or equal 0, then your assumption is correct. Now, you write assumption correct. Now, it asks you about the minimum value. The minimum value is related to this point. Why there is a minimum value for the load? You have to ask yourself this question first. Why there is a minimum value for the load? Okay? Assume that the load is going to be reduced. We are going to decrease the load resistance very much. What will happen? As we decrease the load resistance, the current going to the load will be high. The current going to the load will be high. So this part, this 1 milliampere will increase. It will keep increasing as you reduce. As RL decreases, the current going to the load will increase. And if the current going to the load increases, what happens to the Zener current? So the load current is going to increase. What happens to the Zener current? The Zener current is going to decrease, right? You are subtracting a bigger amount here until the Zener current becomes less than 0. Until the Zener current becomes less than 0. In this case, the Zener diode will go out of the breakdown region. Your assumption of breakdown, your assumption of the Zener diode being in the regulator mode will be wrong. In this case, if you reach to this value, this assumption in this point, assumption will be wrong. So the question here, so this is an explanation of why we have a minimum R. Okay, so the question here is, what is the minimum R? How can we calculate the minimum R? So we will use the condition. In order to calculate the minimum R, what we'll do is we'll say that we need I Zener to be greater than 0. We need R Zener to be greater than 0. And then I'm going to remove this and maybe we'll do it here. So in order to calculate the minimum R, we'll say that we need I Zener to be greater than or equal 0. And I Zener equals what? Let's assume that we don't know R. We need to calculate the minimum R here. Okay? RL. Okay? So I Zener equals what? I Zener equals the current here plus the current here. So it's equal to 20 minus 5 over 5 kilo ohm plus the current coming from the load here, which is 0 minus 5 over R load. Right? This must be greater than or equal to 0. From here, this is 3 milliampere minus 5 over R load must be greater than or equal to 0. We can take this to the other side. So 3 milliampere must be greater than or equal to 5 over RL, which means that RL must be greater than 5 over 3 milliampere, which will be 1.667 kilo ohm. And now this is the minimum value of RL. This will be the minimum value of RL, so that the Zener diode will remain in the breakdown region and it will stay in the regulator mode. Okay? So this is how, if I ask you about the minimum load resistance, or even sometimes I'm going to ask you about the maximum source resistance, the maximum resistance R connected to the source. Why the maximum? Because again, as we increase R here, the total current coming from the source is going to decrease. The total current coming from the source, as we increase R, the total current coming from the source is going to decrease. And if the total current decreases, at certain point I Zener, the current going to the Zener diode, is going to decrease below IZK. And again, the Zener diode will not work in the breakdown region. So there is a minimum for the load, there is a maximum for this resistance. And both of them you can calculate from this condition. From the condition that we need in order to operate in the breakdown region, we need I Zener to be greater than or equal to 0. We'll stop here in this video and we'll see you in the next video, inshallah.